The interstellar object 3I/Atlas, scheduled to pass behind the Sun relative to Earth on October 21st, 2025, presents a moment of profound scientific curiosity and speculation. On that date, the object will enter what astronomers call solar conjunction, meaning it will be positioned directly opposite the Earth with the Sun in between. From our perspective, 3I/Atlas will be completely lost in the Sun's overwhelming glare, impossible to observe from ground-based telescopes even shortly after sunset or before dawn. This temporary disappearance raises questions not only about observational astronomy, but also about broader possibilities, including those entertained in theoretical discussions about extraterrestrial technology or advanced spacecraft behavior. Could such a hideout period provide an opportune moment for a technological maneuver, whether natural or artificial, executed deliberately in the shadow of the Sun? The idea may sound dramatic, but contemplating it requires only an understanding of standard astronautical mechanics rather than science fiction. In spaceflight dynamics, the timing of a maneuver is often as important as the magnitude of the thrust applied. The Oberth effect, a well-established principle in astronautics, teaches that the most energy-efficient point to accelerate or decelerate a spacecraft is at its highest velocity, typically when it is closest to a massive gravitational body. As a spacecraft approaches a star or planet, its speed naturally increases as gravitational potential energy converts into kinetic energy. If an engine burn is executed at that moment, the added velocity compounds more effectively, allowing the spacecraft to gain far more kinetic energy than it would from the same burn performed elsewhere in its orbit. Conversely, slowing down at periapsis is equally efficient if the goal is to shed orbital energy. This effect, though counterintuitive at first glance, is deeply rooted in classical mechanics and has been utilized in many interplanetary missions, from Voyager to modern probes exploring the outer solar system. The physical logic behind this effect mirrors another process found in astrophysics, known as the Hill's mechanism. In that scenario, a binary star system that passes dangerously close to a supermassive black hole experiences intense tidal forces. One star may be captured by the black hole, while the other is violently ejected outward at hypervelocity speeds, sometimes so fast that it escapes its galaxy entirely. The analogy between an engine burn in spacecraft navigation and the astrophysical slingshot of a hypervelocity star is not perfect, but the underlying concept, gaining enormous energy when interacting with a massive gravitational system, is shared by both processes. These parallels offer an interesting lens through which to view potential behaviors of interstellar objects like 3I/Atlas, whether they are purely natural or hypothetically engineered. If in some speculative scenario, 3I/Atlas were a massive extraterrestrial craft or a mothership-like structure rather than a conventional cometary body, its main trajectory might still obey gravitational physics exactly as expected. It would continue moving along its inbound path, swing around the Sun at perihelion, and then head back out into interstellar space. Any probes or subcraft released from it, however, would have opportunities to exploit the Oberth effect during this perihelion passage. If such mini-probes were designed to visit planets or moons within our solar system, releasing them at the moment of highest orbital velocity would minimize the energy expenditure required for them to break away from the parent object's trajectory and curve toward their respective destinations. This hypothetical scenario becomes particularly intriguing when we observe the timing of 3I/Atlas's solar conjunction and its perihelion. Only 8 days after vanishing behind the Sun from Earth's viewpoint, 3I/Atlas will reach its closest approach to the Sun on October 29, 2025, at a distance of roughly 203 million kilometers. The fact that these two events occur within such a narrow window is scientifically fascinating. Solar conjunction renders the object unobservable, and perihelion positions it at the moment of maximum velocity, exactly the combination one might expect if a spacecraft wished to perform maneuvers away from prying eyes. The alignment may be a complete coincidence, as orbital mechanics often produce patterns that appear intentional despite arising from natural processes. Nonetheless, The overlap between invisibility and energetic optimality invites legitimate curiosity, not because it confirms anything extraordinary, but because it challenges us to examine the boundaries of what is possible. Science, of course, does not operate on speculation alone. It is disciplined by data and evidence, and the way to evaluate such extraordinary possibilities is through careful monitoring. The months immediately following perihelion, particularly November and December 2025, will provide the best opportunity for astronomers to search for any unusual activity associated with 3I/Atlas. If the object behaved in unexpected ways, such as releasing secondary bodies or showing accelerated motion inconsistent with outgassing, these anomalies would become more detectable after it moves out of solar conjunction and becomes observable once more. Additionally, if smaller objects were ejected from it during its perihelion passage, their paths would gradually diverge from the primary trajectory due to solar tidal forces and initial velocity kicks. Over a span of weeks to months, astronomers would be able to identify whether any new bodies had appeared and whether their motions could be explained by natural cometary fragmentation or required a more exotic explanation. One of the notable characteristics of 3I/Atlas is its estimated minimum diameter of about 5 kilometers, a substantial size for an interstellar object. At perihelion, the sun's illumination would deliver over 33 gigawatts of power to its surface, a remarkable amount of energy. To put this in perspective, this energy flux exceeds a third of the total output of the 94 operational commercial nuclear reactors in the United States. While this comparison is mainly illustrative, it underscores the immense solar energy available at such distances for sublimation, heating, or any other process that might occur on or within the object. If 3I/Atlas is indeed a natural cometary body, this energy would primarily drive the outgassing of volatile materials. If, however, one were to indulge in speculative hypotheticals, such power levels could theoretically support technological activity of a kind not yet imaginable to us. At present, the overwhelming evidence suggests that 3I/Atlas is most likely a natural comet, an icy visitor from beyond our solar system behaving largely as expected. Yet science has room, albeit a very small one, for low-probability, high-impact possibilities, sometimes referred to as black swan events. Considering such possibilities does not mean accepting them as true. Rather, it encourages observation and preparedness. The idea that an interstellar object could engage in an Oberth maneuver or deploy probes may be extraordinary, but scientific discipline requires us to gather data before rejecting or confirming any hypothesis outright. The Loeb scale, which attempts to quantify the likelihood of extraterrestrial technological origin, ranked 3I/Atlas at level 4 upon its discovery in July 2025, due to a collection of 8 observed anomalies. A ranking at this level does not imply technological origin. It merely flags the object as worthy of careful observation and further study. In the end, the cosmos often surprises us not because it is intentionally mysterious, but because we are still learning how to interpret the phenomena within it. Whether 3I/Atlas behaves as a typical comet or exhibits unexpected features, its passage through the inner solar system offers a rare scientific opportunity. Its temporary disappearance behind the sun, its perihelion proximity, and its unusual interstellar origin combine to create a moment rich with possibility. The responsible course of action is to observe, measure, analyze, and let the data speak for itself. In doing so, we engage not only with the mechanics of celestial motion, but also with the enduring human desire to understand our place in a vast and dynamic universe.